I noticed at lunch today that the number of people had decreased quite a bit, and I'm assuming to catch travel home, or maybe find an excuse to go to New York City. We have a smaller class this afternoon. So if any since it is smaller, if you have questions and you want to interrupt me, feel free to do so. I want to pick up on what I discussed yesterday. If you remember, what I hoped to do yesterday at least was to give you some familiarity with the different types of energetic materials in terms of propellants, explosives, talk a little bit more about pyrotechnics today, metal combustion. But I want to pick it up with, I showed you a couple of the important metrics yesterday, the burning rate and the temperature sensitivity of the burning rate. And I want to give you some idea of where our understanding is in terms of the actual combustion process and the structure of the flames that develop off of the surface. So do a little bit of chemical kinetics, show you a little bit what we know about monopropellants and their decomposition first. And then I'll show you where we are in terms of the state of the art in trying to understand composite propellants, which, as I showed you yesterday, are going to be three-dimensional, very complex to understand. And then in the second lecture, I actually want to pick up and talk a little bit about metal combustion and show you then how that's integrated in propellants and what we know about that. And then in the third lecture, I'm going to kind of show you where the field has been going in the more recent years, particularly with regards to looking at nanomaterial. If you look at energetic materials, and this goes back to the synthesis, all the energetic materials that we typically deal with involve carbon, hydrogen, nitrogen, and oxygen, and I can add a metal fuel. Okay, so as a synthesis, there's only so many ways I can reorganize those atoms. And so there's an upper limit on the energy density of that material. Okay, and usually there's a rule of thumb: the higher the energy density, the higher the sensitivity. I mean, that's one of the big struggles in the field, is if you can somehow understand that relationship and decouple it, you've accomplished a lot. But my point is, if I want to put more and more energy in a propellant to put in a rocket motor, I can only do it so many ways. The field, people have been synthesizing molecular structures, and we're sort of reaching an upper limit. And so where the field now is sort of going is, instead of asking the question, how do I put more energy density into the material, how do I control the material's burning characteristics, its sensitivity better? And that has to do then with the organization of how I build up the structure. Can I actually have a propellant that I want to turn on and turn off? Can I change its characteristics on the fly, to change it from a deflagration to a homogeneous explosion? Can I put the propellant out, as I said? And so it's really a matter now of looking at how can I change its reactivity and its characteristics to make use of it better than trying to get more energy density into the system. So let me pick up, and as I said, the first thing I want to talk about today is to introduce you to a little bit of our understanding in terms of the chemistry of these energetic materials. And I'm going to, that's not the one I want. I'm going to start first by looking at, as I said, monomolecular type compounds that are homogeneous. That's the simplest to look at in terms of the chemistry characteristics. So to go back and just to refresh our memory here, these are going to be pre-mixed systems. In terms of their reaction, they'll be kinetically limited, not diffusion limited, since it's a homogeneous material. Typical examples: nitrocellulose, nitroglycerin, all the nitrate esters, the nitramines. But I showed you an example of even a high explosive yesterday, the PBX9501. And I showed you that there's very little binder in that system. So even often that system is considered to be a homogeneous system with just the HMX in it. And obviously molecularly mixed materials like double-based and triple-based can be considered as homogeneous systems. They can be broken up in terms of their chemical hydrocarbon backbone. And so here, if you look at the typical aliphatics, what the oxidizer form can be in typically 3 different forms: as a nitro group, as a nitrite group, as a nitrate group, or as a nitramine. And these typically are then bonded to basically an alkyl radical. So in the case of nitromethane, I replace one of the hydrogen atoms with the nitro group. In the case of methyl nitrite, the hydrogen atom's been replaced with the nitrite. So this is really, these two are just really isomers. And then in case of methyl nitrate, I introduce the NO3 group. And you can do that for all, I can do that for ethyl, propyl, butyl. So I can have nitrobutane, nitropentane, etc. A couple other examples: nitroglycerin we looked at yesterday, nitroguanidine. This is having the amine groups with an NO2. If I look at cycloaliphatics, this basically includes your nitramines. So here I'd have RDX and HMX. Typically when I draw it out, this is, as I said yesterday, this is a 6-member ring, 8-member ring with alternating carbon and nitrogen with the NO2 groups off the nitrogen. These are not flat structures. They actually have different polymorphs, and as a consequence of that, they have different solid phases. And those solid phases, the energetics, when I go from one phase to another, is important in terms of the combustion process as well. Aromatics are based on the benzene ring. Trinitrobenzene, TNB, I replaced 3 of the hydrogen atoms with NO2 groups. We looked at TNT yesterday, looked at TATB yesterday. And so again, making use of the benzene ring structure instead of just a cyclic compound, and adding NO2 groups. Inorganics, these don't make use of basically the hydrocarbon backbone. So they're ionic compounds typically, and the most common are ammonium nitrate, ammonium perchlorate, AP, potassium chlorate, or potassium perchlorate. Okay, so here I've got the chlorine atom in the system, and what you'll typically see when the reaction initiates here, there's going to be a proton shift from the one side, for example here the NH4 to the NO3, and I'll end up forming ammonia and basically an NO3H compound. Yeah. Yeah. Yeah, ammonium nitrate is, it's not as energetic, but that's what Timothy McVeigh used. Yep. There's some newer compounds. These are some of the more recent synthesized type materials, and again, they're mostly ionic. The interest in ionic compounds I mentioned yesterday is they have low vapor pressures. So if they're going to be used as rocket propellants in space, then the fact that I have the low vapor pressure, it stays pretty much intact. Ammonia dinitramide, hydroxylammonium nitrate, and as I mentioned yesterday, this is Cl20. I'm not going to try to pronounce that, but this was probably the most recent synthesized material that's now starting to be in use in some propellants, and its compound is the highest energy density in an organic type compound. You can have cubane type compounds as well. Even more recently, high nitrogen compounds. I show a couple here, but this shows a wider variety of them. And the most typical are azides, but azides are very sensitive. Less sensitive nitrogen compounds are your tetrazoles, tetrazenes, and furazans. And what's interesting about these compounds, they get basically their energy from the fact that I have singly bonded or doubly bonded nitrogen atoms in a ring structure, that when the ring structure comes apart, I'm going to end up forming triple bonds to form the molecular nitrogen, and that's where a significant amount of the energy is going to come from. They also typically have a significant amount of hydrogen bonded into the system, so they're largely high nitrogen compounds. So the final products will have pretty well low molecular weights. The molecular nitrogen will be 28, and molecular hydrogen, obviously, 2. And with regards to the other reasons, with regards to the high nitrogen compounds, is they start to disobey that rule that I just told you about the relationship between the energy density and performance and the sensitivity. You're seeing that correlation start to come apart. They also have very high burning rates with a very low pressure exponent. Some of them have pressure exponents below about 0.2, so they show no pressure dependency. And they can detonate without having any oxygen. I'll show some examples later on. They can burn rapidly without a visible flame. And as I mentioned, they have very high hydrogen contents. Okay, so there's some of the examples of what look like these pure substances, homogeneous substances. And these are the type of compounds that researchers have been trying to develop models for and understand how they come apart and burn. So I want to go back and talk a little bit about some basic chemical kinetics and how one might start estimating how reactions would be initiated and how they might differ from hydrocarbon oxidation. So if I look at typical reactions that occur in energetic materials like those I just described, the simplest type of initiation process is just a bond scission process, okay, and that's going to be related to the bond dissociation energy. And I can look at the bond dissociation energy if I have a compound AB and I want to break this AB bond. The bond dissociation energy is just the difference between the heat of formation of the compound AB and the heats of formation of the individual fragments. Okay, and it's useful to start tabulating the bond dissociation energies to find the weakest in the compound, because that's likely where the reaction is going to be initiated. And so if you do that, I give a couple examples here, but I'll show you some more in a second. If I look at the bond dissociation between a carbon and an NO2 group, and I compare it to a carbon and just an NO group, I can see this bond with the NO2 group is going to be larger than with the NO group. So this is the Nitroso compound versus the Nitro compound. If I look at the bond dissociation energy between two nitrogen atoms, the nitrogen in the ring structure, say, with an NO2 group, and I compare it to, again, the nitrogen with the Nitroso group, I find that the bond energies are very much the same order. So there's not going to be any preference in terms of the initial decomposition. And I'll show you a listing of some values of this in the next slide. What happens next, obviously, if I dissociate NO2 from the original compound, I'm left with a radical, okay? And that radical can continue to dissociate by bond fission. If that happens, you can again go back and through and calculate the bond dissociation energies for each of the bonds in that radical. And what you'll typically find is those dissociation energies are going to be different and typically lower than in the original compound if I looked at that same bond. So it's important to start, if I start with a stable compound, I go to the radical, recalculating what those bond dissociation energies are. An unusual reaction that one sees at very high heating rates is what's referred to as concerted decomposition. So this is where I potentially have some sort of ring structure, either something like RDX or HMX that I showed you, or even a simpler case where I have trioxane, which is just 3 formaldehydes in a ring here. And what happens is the energy becomes distributed throughout the molecular structure, and 3 bonds break nearly at the same time. And I end up with, in the case of trioxane, it breaking apart to form 3 formaldehydes. And in the case of RDX, it breaks apart to form 3 methylene nitramine molecules. And so I don't have, a slow process of it coming apart. Basically, the ring unravels in one step. Another type of process is a complex fission process. All these compounds have NO2 typically around the ring structure. And what the NO2 can do then is it can wrap around in what's referred to form a 5-membered complex. And the oxygen atom on the end of the NO2 can basically grab a hydrogen atom from one of the carbon atoms and eliminate HONO as an initial step. And I'll show you an example of that as well. You can have autocatalytic steps. This is more common, what you'd see in hydrocarbon oxidation after a radical pool has been formed, where a radical comes back and abstracts or adds to the molecular structure. These processes typically have lower activation energies, so once the radical pool gets established, they can be competitive with a decomposition reaction. And I'll show you something that also shows up at very high pressures, or what could potentially show up in now condensed phases, where some of the products being formed can actually act as a catalyst and assisting the decomposition, which is kind of unusual in oxidation and decomposition processes. Okay, so here's a short table with just a few bond dissociation energies, and I tried to break it up into different categories just to kind of give you a feel for how they could be used and what you might see in terms of how the reactions would be initially decomposed. So in this column here, I'm looking at the Nitroso compound. So this is where I have NO basically bound to a carbon or a nitrogen or hydrogen atoms. And the second group here, it's the Nitro compound, so it's NO2 bonded to this similar alkyl radical or amine group or a hydrogen. In the third group here, this is the nitrate compound, so it's really similar to the second group, but where I just have the isomer, and now the oxygen in the NO2 group is attached to either the alkyl group or the amine group. And then the third group that I just show a couple on is the nitrate group, where I have NO3, and it's the oxygen that's typically bonded to the carbon, the nitrogen, or the hydrogen. Okay, so you can look through this, you can see the values change drastically, and it's kind of interesting, you know, for example, if I look at nitromethane here, CH3NO2, so the bond energy for breaking the CN bond here is like about 59 kilocalories per mole. If I go over and look at its isomer, CH3 ONO, and look at the CO bond breaking, it's very similar, about 57 kilocalories per mole. But now, suppose I did have this isomerization step, and I go back and I say, well, how strong is the ON bond versus the CH bond? Well, I can come back over here, and this is the same compound, and I look at the bond strength of the ON bond, and I see it's considerably lower. Okay, so now this is going to be the bond that's going to really break in the system. I'm going to end up forming methoxy and NO in the system, if I can go through the isomerization step, or if I start off with the nitrate. I can also go through and look at what's the difference between, say, nitromethane and methyl nitrate and methyl nitrite. And you can see here, if I look at the CN bond here, again, it's about the 59 I mentioned. If I come over here, it was the 57. And if I come down here, the CO bond here is considerably larger. So in this case, if I'm looking at methyl nitrate again, if I come over up here, so this is the ON bond instead of the CH bond, and you can see the ON bond is considerably lower than the CO bond. So you can start to see where these molecular structures are going to start to dissociate. Okay, so let me show you now an example of, I mentioned this HONO elimination reaction, how that can be competitive in the system as well. So this is a potential energy diagram that as a function of the reaction coordinate, the energetics for the reaction to proceed. And I'm looking at three cases here, methyl nitrate, methyl nitramine, nitroethane, and methylene nitramine. Okay, and what you're looking at is two different types of reactions. The one on the top here is going to be if I have a bond scission reaction and I just dissociate one of the bonds. So as we just saw, the weakest bond and the methyl nitrate is going to be the ON bond, and its barrier is going to have a value of about 40 kilocalories per mole. Okay, and if I look at the other compounds, for example, the methyl nitramine, the weak bond is going to be the NN bond, about 51 kilocalories per mole. The nitroethane, the weak bond is going to be the CN bond, 61, and the methylene nitramine is going to be the CNO2 with about 70 kilocalories per mole. What becomes competitive with these simple bond dissociation reactions is this HONO elimination process, where I have, as I said, if I have something like this, I can start making a ring structure here where this oxygen starts coming over here, and I start bonding here. And what happens then is this bond becomes weak, this bond becomes weak, and I end up with formaldehyde and HONO. So forming a ring structure that then eliminates HONO in the system. And if I look at that sort of process, you can see now, to form the adduct, I have an activation barrier of about 33 kilocalories per mole. And if the adduct then comes apart, the overall energetics are exothermic. So now, looking at these two different processes that could occur, this is a very endothermic process in the end. This is a very exothermic process with a lower activation barrier. And I can go through the same sort of HONO elimination for all these different reactions. Well, what's it mean practically? Well, it depends on the heating rate and how fast I get to temperature. If I get to temperature and the heating rate's very high, then what I'm going to find is the bond dissociation is going to be favored. But if I'm at a lower heating rate, lower temperature, then the HONO elimination is going to be very competitive. It's exothermic, but it's going to have a lower A factor in terms of an Arrhenius rate constant. Okay, I mentioned the autocatalyst reaction. Again, these are simple abstraction reactions or addition reactions. So here's methyl nitramine again, and suppose I have a reaction with a hydrogen atom. If it's an addition reaction, I can form an adduct as shown here where the H atom's been added to the oxygen, and I have a structure that looks like this. And then the adduct can decompose in many different forms at different energy levels. If I just pick out one example, I could have the NN bond break here, and I end up following this path here to form HONO and CH3NH. And so this barrier height here from the adduct up to here is about 10 kilocalories per mole, and to form the adduct, it was about 10 kilocalories per mole as well. Okay. If I go back and I compare, if I start off with my methyl nitramine and I wanted to break this NN bond as was done here, if you remember from the previous slide, the bond energy here was about 60 kilocalories per mole. So what that indicates, once I start obviously getting a radical pool started, then the bond barriers for reaction, the activation energies become lower, and I start favoring then the autocatalyst reactions with radicals. I can also have a simple abstraction reaction where the hydrogen atom may come in and off the methyl group abstract an H atom and form molecular hydrogen. So these type of reactions are very similar to hydrocarbon systems. But once the radical pool becomes built up, they become competitive. Now I did want to show you something that's not found as often in a hydrocarbon system, and this is where some of the products can start to become a catalyst in the system. This could become very important, as I said, in condensed phase reactions, and if I get to very high pressures where you start seeing a caged effect and the collisions between molecules and systems are sort of restricted to what's in the vicinity right around them. And so here's a case where I'm looking at essentially nitramine, NH2NO2, and I want to look at its conversion to make nitrous oxide in water, basically through this acid form of the nitramine. So imagine now I've got a water molecule colliding with the nitramine, and as it comes closer, what I end up doing is start to form what looks like a complex again. The proton H here gets transferred to the oxygen here, and the hydrogen on the amine gets transferred to the oxygen of the original water, and I end up in the products then just having water again. But what I've done is really gone through an isomerization process where the hydrogen atom has moved across, and now it's to form a hydroxyl group to form what's referred to as the acid form of the nitramine. Now again, if the water is in the vicinity again, I can go through this proton transfer process again at relatively low activation energies. This hydrogen atom can be transferred to the oxygen atom here, the hydrogen atom on the NH group transferred to this oxygen on the original water, and it comes apart then forming now two water molecules and an N2O molecule. These type of processes, when you look at the decomposition of nitramines and nitrate esters, what you'll typically see at very low temperatures is in the products aldehydes and N2O. If I go to higher temperatures, I typically find HONO and HCN. Okay, so there's a difference of what's being formed, and these are the type of processes that might start suggesting the low temperature reactions to give me the nitrous oxide route. Okay, so just to give you, again, an idea of what's been done in the field, it's very similar to the hydrocarbon field. People have measured experimental rate constants of different types of elementary reactions. As they get more complicated, basically ab initio quantum mechanical approaches are used to calculate the structure of the adduct that's formed, and also the bond energies calculate the heats of formation, the Gibbs free energies. And if I know the structural information about the molecules, I can use transition state theory, I can use variations of RRKM theory to calculate essentially rate constants. And as I build up this, I can start building up a reaction mechanisms of many reactions that would start to describe the process of taking the original molecular structure and converting it to final products. And so this sort of shows the hierarchical process that people have typically used in the past to do that. There's typically a component that just conducts experiments and a component that has analogous type modeling type studies. So the path I show over here is just what I said: go to the laboratory, try to measure individual rate constants of reactions. Once I develop the mechanism, I start conducting types of experiments to follow the entire mechanism in a time-dependent process where I look at the initial molecular structure as it goes through and forms intermediates and final products as a function of time. And finally then, these may be in dilute cases where I decouple the heat release, so I don't look at the temperature feedback and changing the rate constants. And then as I go up to the more complex systems, I start taking away the fact that they may be dilute mixtures. The temperature in the system's changing, so now I have a temperature feedback changing the rate constant. It starts changing the structure. If I put it in a system like a flame, a diffusion flame or a pre-mixed flame, I also have to account for transport processes. So the molecular diffusivities have to be accounted for in that. And so the complexity gets more and more complex, and at each step, I develop an analog model to see whether or not I can predict those experiments. And that's one mechanism then of developing a validated system. And the idea of using different types of complementary diagnostics to measure different species, temperature, and performing analysis on the model, sensitivity analysis, to find out which are the rate controlling reactions to design experiments, specifically look at the most uncertain parameters in the system. With regards to what type of mixtures I might study to learn about these systems, again, Charlie Westbrook and Fred Dreyer very early on in hydrocarbon oxidation developed this hierarchy scheme where if they wanted to look at an alkane oxidation process, they'd look at the sequence in which it was reacted, and very late they'd see as the alkane gets oxidized, eventually it forms carbon monoxide and hydrogen, and the last step of the oxidation process was to convert the hydrogen and the carbon monoxide to CO2 and hydrogen. And so the hydrogen mechanism and the carbon monoxide mechanism ends up being a subset of all hydrocarbon oxidation mechanisms. So the idea was, okay, well, let me start validating and understanding the hydrogen mechanism first, then the carbon monoxide mechanism, then the formaldehyde mechanism, then the methane, the ethane, the propane, and so forth. And they could build and just add reactions as necessary to assuming that the ones that were already in the mechanism were well defined and would not have to be altered later on. And so you see this sort of hierarchical process, first developing mechanisms based on the procedure I showed you in the previous view graph, first developing hydrogen, oxygen, then developing a CO mechanism, a formaldehyde, ethane, propane, and et cetera. You can apply the same sort of idea to nitrate esters and nitramine chemistry. What you typically find again is as I go through this process, the hydrogen NO2 mechanism or hydrogen N2O mechanism are what occur late in the oxidation scheme. So I would start off and make sure I understand that chemistry early on, because that's going to be some of the chemistry responsible for developing the radical pool, and it's going to occur no matter if I'm looking at RDX, HMX, nitrocellulose, or whatever. So I've got to have a good understanding of that. As I understand that, if I wanted to study, for example, RDX, the next mechanism I might look at is to add carbon monoxide to this system and make sure I understand that, formaldehyde, and then start moving up the system. And if it was, studying nitromethane, I'd continue up this way. I'd study methane and eventually nitromethane itself. So this sort of hierarchical process in developing reaction mechanisms. Just to give you an example of that, one example of using a flow reactor back here. These are some studies that we actually, Fred Dreyer and I conducted here at Princeton a few years back, where in the flow reactor, it's just run as an isothermal system where I develop a flow through a tube, and it's mostly an inert gas like nitrogen, and I add a small quantity of reactants. such that when the reactants react, there's really no heat release, so the temperature stays nearly constant. So it's an isothermal system. So I don't have to worry about the rate constants changing. All I need to do is look at how the reactions are proceeding through the system. So as I said, one of the early systems that you might want to study is the nitrous oxide decomposition. And here, as a function of time or position in this tube, the gases are sampled with a sampling probe and extracted, and they're measured. And I convert, knowing the velocity, the position, into time. I can basically make plots of how the N2O is disappearing, the forming molecular oxygen, NO and NO2, and then develop models to see how well it predicts those experimental results. If I change and now add a fuel to this, for example, methane and nitrous oxide, doing the same sort of experiments, you'll see the methane disappear, you'll see the nitrous oxide disappear, and now you start seeing a number of intermediates being formed before I get to the final products of water, CO2 or carbon monoxide, and hydrogen. And again, I go through this sort of validation process of the mechanism, and I continue working up to more and more complexity. But recognizing that these submodels are going to be valid to many, many different types of larger molecular species. Okay, so if you do that, what you can do now is go back, and I showed an example of a mechanism that was developed for nitromethane. Okay, this is a simple homogeneous box where I have nitromethane in it. It's a constant volume type calculation. It was initiated above the ignition temperature, above about 1,000. It starts out about 1,000 Kelvin, and then I proceed and I watch how the kinetics develop in the calculation. And this is what I'm showing you here is very classic of nitrate esters and nitramines. So you'll notice here, initially the reaction starts, I'm plotting here temperature versus time, and you see the temperature stays nearly constant, and then all of a sudden an exothermic reaction occurs. And then it raises to another temperature. Then all of a sudden it appears that the reaction stops, and I have a period before a second reaction begins, and I go to the final temperature. So I have this multi-stage characteristic. And this is typically referred to as the first stage here. This is referred to as the dark zone, and I'll show you why it's the dark zone. And this is a second stage reaction here. And the chemistry then changes as I proceed through this sort of reaction. But the type of chemistry that occurs here is very typical of all these systems. So if you look at the associated concentration profiles of the different species in this system, you'll see something that looks like this. So the nitromethane will start coming apart. The weak bond, again, if you remember, if we went back, is going to be the CN bond, so I'm going to form a methyl group and an NO2 group, and the question then is, well, how does the NO2 now react with the methyl radical? Okay, and typically what happens then is the two join together. I can end up forming the isomer to go back and form the nitrate, or I can take the methyl group can abstract one of the O atoms off of the NO2 to form methoxy and NO. And as it proceeds then, eventually I go to formaldehyde here. I end up forming some methane, and this is the region, the first stage reaction, and this region right here is the dark zone, and then where you see the reaction occurring out here is the second stage reaction. And for most purposes, what's happening in the dark zone, you'll see it later, I end up taking that NO2 that came off here and I quickly convert it to NO. And NO has very slow oxidation kinetics, reduction. And so it sticks around. It's very difficult to form molecular nitrogen. So it goes through a process of forming nitrous oxide and hydrogen cyanide, which is very slow until I proceed out here. And eventually I get out here, the hydrogen cyanide, and I'm not showing the N2O here. I end up forming in the last stage, the second stage, molecular nitrogen. And you can go through then and follow, for example, the carbon atoms, the nitrogen atoms, the oxygen atoms in each one of these stages and look at the dominant reactions that are occurring. And without going into too much detail here, if I look at the first stage chemistry and I follow basically a reaction diagram, here's my nitromethane, and through a dissociation step, if it's not in this high pressure limit, any other body comes along, transfers energy to this nitromethane, breaks the CN bond, and I end up with basically looking at the carbon chain, basically a methyl group. And then the methyl group can actually have the NO2 come back and add to it to form the nitrate form, or it can go through and react with the NO2 that just came apart to form methoxy. And if I form the nitrate, again, now the weak bond's going to be the ON bond, which is going to end up forming the methoxy anyway. And eventually then the methoxy, if it collides through a dissociation reaction, I'm going to lose an H atom and it's going to form formaldehyde. So this is typically what happens in the first stage. The methyl radicals can also go back that I formed initially and start forming methane. So you saw a little bit of methane that was formed, as well as methanol. And some of these steps become very important because they provide exothermicity to keep the reaction going. For example, the formation of the methanol here actually releases a significant amount of heat that's necessary to proceed the reaction. If you look at the nitrogen chain, then, as I said, I'm going to follow what happens to the nitrogen atom. It makes NO2, it goes through the nitrite, and eventually it ends up as NO. And that's where most of it stays, because you can see in this stage here, the forward reaction and reverse reaction are pretty much equilibrated between HNO and NO. And so it's stuck mainly as NO. And now the question is, how does it get converted to N2? And so you can do this, you can look at the dark zone chemistry and follow again. I don't want to spend much time here, but you can see in the dark zone, I did form some methane at the end of the first stage. That goes through basically forming methyl again, and eventually it's going to form HCN. If I follow the nitrogen process at the end of the first stage, as I said, you had mainly NO, and as it goes through into the second stage, I start to form HCN. And if I look at the last stage, the second stage chemistry out of the dark zone, then the HCN eventually gets converted to CN and goes through a number of processes, much like Raprinox in a hydrocarbon system, to form CO and CO2. If you form and just follow the NO portion of the nitrogen, it ends up going through N2O to form the molecular nitrogen. In a very similar way, if I start off with the HCN, it ends up going through a number of different steps to eventually form N2. So it becomes a very complex process. But overall, if you were to look at this system, I started off with the original species that had maybe an NO2 group or an ONO2 group. I end up forming NO2, and I form either a CH group or an aldehyde group. I then go into, and out of that, I basically form NO and CO formaldehyde, and the dark zone is converting that NO to more useful species that will eventually lead to forming the N2 in the second stage. And so if I look phenomenologically then at the flame structure of what a double-base propellant might look like, just going back and looking at that nitromethane, this is what's typically you would see, even for nitrocellulose nitroglycerin. So I'd start off with my nitrate group like this on some sort of alkyl radical. The weak bond's going to be the ON bond here. I'm going to end up forming an aldehyde and the NO2. So if I look at the structure, there's very little reaction in the in-depth in the solid phase here. If I get near the surface, there could start to be some melt layer and there some condensed phase chemistry. I then get to what would be like a surface. Off of the surface, I get into what's referred to as a fizz zone, or the first stage reaction, and that's where the NO2 is converted to NO, the aldehyde is converted to CO and hydrogen. And then I go into this dark zone here, where it's very difficult to reduce the NO to N2, and so I go through a number of processes of making HCN, N2O, and eventually in the second stage reaction, that NO gets converted to N2, and any remainder carbon monoxide that would be converted to CO2 because of the stoichiometric gets finished off. Okay, so this is very typical now of any nitrate ester, nitramine type propellant, this multi-zone characteristic, and the phenomenological chemistry that I show you here is going to be true in all those systems. Okay, so I've talked about this dark zone, and just to show you its existence, here's some experiments on nitrocellulose nitroglycerin, and they're done at 3 different pressures here, like 10 atmospheres, 20 atmospheres, and 30 atmospheres. And if I look at the double-base propellant, very near the surface here, you can see some luminosity. That's the first stage reaction, very close to the surface at the low pressure. Then I have this region where there's this dark zone, and then I come into the second stage reaction where I see luminosity again. As I increase the pressure, the length of the dark zone starts decreasing, so the second stage reaction is catching up to the first stage reaction. It changes the heat feedback to the surface, and I essentially change the burning rate then. Okay, and so you can make a plot, and this is just showing here as a function of pressure, how the dark zone shrinking in size and the second stage reaction getting very close to the surface. So there have been research on developing reaction mechanisms and calculating the flame structure double-base propellants. Typically in these systems, one still does not understand the condensed phase chemistry, and that condensed phase chemistry is typically ignored. But as a consequence of that, in terms of modeling these systems, what's done is to assume that all the reaction does not occur in depth in the condensed phase, but if there's any condensed phase reaction, it occurs on the surface, okay, along with a vaporization step. Okay, so to model it, I need to know something about what's coming off of the surface then, and the rate at which I'm basically pyrolyzing or reacting at the surface. And what people have done is they've conducted different types of pyrolysis type experiments where I might take a small sample of the material and put it on a film that's resistively heated. And I raise the temperature of that film to a certain temperature, and I hold that temperature, and I look at what's coming off of the surface. I have a mass spec, or I have some sort of Fourier transform infrared analyzer measuring the species coming off the surface, and I measure the weight change of how fast I'm basically eliminating mass from the surface. And that allows me then to create what's referred to as a pyrolysis law. And if you remember from yesterday when I was talking about the burning rate, people often correlate the burning rate to something that looks like an Arrhenius factor. That's this pyrolysis law here. So from gathering information on that, I can correlate, for example, the mass evolution at the surface to some sort of Arrhenius factor where there's a pre-exponential factor and some sort of activation energy over a gas constant, divided by the temperature. And this is going to be then equivalent to the mass burning rate. So I can get this information from separate experiments. They may be as simple as, I take the strand and I just let a hot plate come down to the surface and let it hit the surface. I know the temperature of the hot plate, and I look at how fast then I remove material from that surface. Or, as I said, there's different types of thermolysis experiments. People have actually deposited, in addition to films, people have deposited a thin film on an electrical wire, and I rapidly heat the electrical wire, and I look at what evolves off the surface to look at what the speciation is at the surface. To show you an example of that then, as I said, that's one mechanism by which one gets the condensed phase. The detailed chemistry is rather well known for these systems, at least at moderate pressures. And so detailed mechanisms are put together using that sort of pyrolysis law and measurements of what comes off the surface. One can develop a reaction mechanism and do a 1D model calculation. I don't show the equations, but if you go to that appendix in Chapter 7, I show example of the types of equations that are solved, typically the energy equation and the species equation and the condensed phase and the gas phase, and they use the surface then as a matching condition. So I'll show you the results of one set of calculations. Miller and Anderson were at the Army Research Laboratory. They've looked at a whole host of number of different types of double-base propellants. I'll show one example of the results. And what you see is something like this. This is for JA2, which again is a nitrocellulose nitroglycerin propellant. They measured a pyrolysis law to get the evolution of the mass at the surface, and they correlate that to a surface temperature, so that becomes sort of a boundary condition. And using the thermolysis experiments, they estimate what the species might be coming off the surface are, and they use this then as a boundary condition. And you can see then their calculations are shown here with the dark symbols, and experiments are with the open symbols and this solid line up here. And over this relatively wide pressure range, they do a relatively good job at predicting the burning rate. But this isn't really surprising because it's very much like in hydrocarbon oxidation. It's relatively easy to calculate the flame speed of a hydrocarbon oxygen system, because it really just depends on knowing the rate of energy release. Knowing the details of the intermediate species are not that critical if I can just get the rate of energy release. And it's the same thing that's true here. If I know how, the rate at which the temperature is rising as a function of distance off the surface, I get a pretty good calculation of the burning rate. But in addition, they did model some of the species and temperature, and you can see here, this is a plot of the temperature profile, and again you can see this multi-stage, the first stage, the dark zone, and then the second stage reaction. And using absorption techniques, either absorption with NO or hydroxyl radical, they were able to back out temperature profiles in different regions, and you know, the calculations do a relatively good job of predicting the temperature profile, you know, qualitatively. And if you look at the NO profile, you can see it's formed at the end of the first stage, and during the dark zone it's slowly consumed, and when I get into the second stage it's quickly consumed. And the model predicts, again, you know, relatively the experimental data. Okay, so this is very typical of nitrate esters. The other example I want to show you is basically nitramines, because the nitramines have probably been studied the most in terms of pure components. And the way, probably the system that's been studied the most is RDX. And again, going back to what I showed you with regards to the type of reactions that occur, these are sort of the three different types of steps that have been assumed that occur and that have actually been measured. Basically the bond scission, where I have on the ring the nitrogen atom and I bond scission with the NO2 group off of it, and I'm left then with this residual radical RDR, which looks like this here. And then the question comes about, well, how does this structure, which is still in a ring, how does it start to open up? I can have the concerted decomposition of the ring, where very quickly, if energy is put into it very fast, I end up breaking 3 bonds nearly at the same time, and I form this methylene nitramine molecular structure. Or at a lower heating rate, I can go through a process where I start to have this HONO elimination. Remember, there's on the RDX, there's 3 NO2 groups, and adjacent to each of those NO2 groups is a carbon atom with 2 hydrogen atoms. So I can successively form these 5-member centered rings and eliminate 1 HONO, then I can eliminate a second HONO, and I eliminate a third HONO, and I end up with a very small structured ring structure left. So here's some examples, just looking at, again, bond energy of this system. Okay, so if I go through and I calculate bond energies in RDX, the weakest bond is going to be the NN bond. Okay, it has a bond energy of about 49 kilocalories per mole. So I'm going to fragment the NO2. So I'm going to have NO2 come off it. And I'm going to be left with this radical structure here, because I've got a radical site here. Now I go back and I calculate with this radical structure, what is the next weakest bond now? Okay, and what I'll find then is the next weakest bond is 1 bond removed from the radical site. Very much the similarity to the beta scission rule and hydrocarbon oxidation. So you can see that this bond, this is the radical site here, 1 bond removed, the bond dissociation energy is like 28 kilocalories per mole. So that's going to break next. And at that point, the ring starts opening. Okay, and I ask the question, well, what's in the remainder part of the fragment of the ring from here over to here, what's the next bond? Well, again, this is going to be the radical site, so it's 1 bond removed, and it has a bond dissociation of 16 kilocalories per mole. So this breaks here, and then finally this breaks over here. And so what I'm left with then is, after the NO2 comes apart, I've got 2 of these methyl nitramine groups, and I'm left with H2CN. Okay, and if I can then look at those individual fragments and ask, well, what are the weak bonds in that? If I look at the methylene nitramine, the weak bond is going to be the NN bond, that's going to break here. If I go again and look at the next weak bond after that, that's going to be the CH bond here, and I'm going to be left then with HCN. And if I look at this structure, the same here, here's my radical site, 1 bond removed is this bond here, that's the weak bond, and again I'm left with HCN. So I end up forming 3 HCNs at the very end after this falls apart. And people have done more sophisticated calculations now, actually going in and using ab initio molecular dynamics. This is, again, a potential energy diagram of that reaction sequence for the breakage of the NO2 bond. And what the more sophisticated theory shows, after I break that initial bond here, the NO2 bond, how the ring structure opens up can actually vary than what I showed you in the previous. It's not quite as simple as just going around and looking at bond energies. So the way the ring opens up can change, and I can end up, from these calculations, showing that there's actually 3 product channels. Okay, the second one here is kind of what I showed you in the previous view graph, but depending on how the ring breaks apart, I can end up with different products that have an overall heat of reaction that varies. Okay, and so the step with the lower heat of reaction, depending on the activation barrier, may proceed. I can also look at the same sort of calculations for HONO elimination. And again, what you see is what I mentioned to you earlier. In the first step here, you see the NO2 group come around, form a 5-centered ring structure, grab an H atom, and eliminate HONO. And I'm left still now with the ring structure intact. And what can change at this point now, from what I just mentioned to you, I can have the second NO2 go around and grab another hydrogen atom, eliminate a second HONO, which would be this down here, or what these calculations also suggest that at this point I can actually open the ring structure. And so as I go through this reaction sequence, depending on the energetics, different processes can actually occur. So, you've got to account for all these sort of steps. But if I go through and look at the eliminating the 3 HONOs, I end up with triazine here, and that triazine is a ring structure, and I can then go through that concerted decomposition to form 3 HCN molecules. Okay, so the gas phase chemistry for these nitramines, RDX and HMX, based on what I just showed you, have been relatively well studied, particularly the secondary chemistry as you go further away from the surface. Those initial steps that I just showed you are now relatively well understood. They've been studied in quite depth by the group out at Caltech. Of all the propellant systems, the system that's had the most study in the condensed phase is RDX. And so the question is, how has that been done? Well, it's been mostly done experimentally, and I show you 3 types of experiments that have been done here. And what's the difference in these experiments is the heating rate. Okay, and the heating rate is very important then in determining what comes out of the surface and what type of condensed phase chemistry happens. So if I'm looking at a relatively slow heating rate, this would be like a cook-off process, where maybe I have an energetic material sitting out in the field, it gets hot one day, and so the temperature starts to rise, and it rises enough that I start to have some chemical activity and I start to decompose the material. So that's that's a condensed phase process that's happening at a slow rate. And so these are experiments that are typically being conducted in basically a thermogravimetric type analyzer, where I measure the weight and the energetics, by a differential scanning calorimeter, and look at how the thermal behavior occurs. In addition to this, one wants to know what's coming off the surface, and so molecular beam mass spectrometry has been used to then, as a function of time, as a function of changing the temperature at these low heating rates, what's evolving out of the surface. And I use that information then to try to back calculate what's happened in the condensed phase then. At a slightly higher heating rate, about 10 to the 3rd K per second, this is very typical of a deflagration. If I have a flame sitting off of the surface, what's the heat feedback going into the surface? And so 10 to the 3rd is relatively representative of that. And a number of different types of experiments have been developed for that. This T-jump FTIR experiment is one that I just described to you, where I have a foil, I resistively heat it, I bring it up to a temperature, I hold that temperature, then above the surface, the ambient may be at low pressure or it's a cold environment. So once the species come off of the surface, they no longer react or quenched, and I use the Fourier transform infrared analyzer to measure the composition and look at how that changes with time, and that gives me some information for what's going on then in the condensed phase. At these higher rates, about 10 to the 7th Kelvin per second, lasers have been used to heat the sample very quickly. And that's more representative than, say, of an explosion or detonation. Okay, and again, depending on the heating rate, you see different types of phenomena at the surface, and the condensed phase chemistry could change. And so, as an example of that, if I do that experiment that was at the moderate heating rate, the T-jump experiment, and I raise the film temperature up to these temperatures here, what you see for both RDX and HMX, at very low temperatures, looking at the ratio of N2O versus NO2, and if it's NO2, it's sort of equivalent to HONO, you find that the dominant type of species coming off the surface is nitrous oxide. Okay, and then you question, well, how is that formed? Is it something like that catalyzed reaction that I showed you earlier with water? But as I go to a higher temperature, a higher heating rate, what comes out of the surface looks more like NO2 versus N2O. Okay, or HONO. So the condensed phase chemistry is actually changing. The activation energies of different processes in the condensed phase change with temperature. So at the early stages, what people have done to develop models then for the condensed phase is basically take and develop empirical models. Much like I told you, in the early hydrocarbon oxidation stage, one postulates a simple reaction, and then they use the experimental data, they fit it to get Arrhenius parameters. And so the idea here was for RDX or HMX, let's assume there's two types of steps, a low temperature step and a high temperature step, a high heating rate step, a low heating rate step. At the low heating rate, I form nitrous oxide and formaldehyde. At the high heating rate, I form HONO and HCN, which is kind of what was evident. And if you look at the energetics, then the low temperature step is exothermic, the high temperature step's endothermic, and as a consequence of that, if you look at the empirical activation energies, what you find is this step here has a lower activation energy versus the high temperature step, which has a higher activation energy. So as I go through from a low temperature to a high temperature, the low activation energy step is going to be favored at low temperatures, and as I get to high temperature, the high activation energy step will be favored. And this is what was used early on then in modeling RDX and HMX. Now, more recently, probably within I'd say the last few years, there's different groups starting to look at how can I study in more detail what's going on in the condensed phase. I showed you these empirical models that are being developed. And what people are now starting to try to look at is, can I go back and start using ab initio quantum mechanical calculations to try to understand the condensed phase? And they do that by basically using solvation techniques. They basically assume that the material's in a solute like water as the solvent. And by doing that, they can start looking at the chemistry again. And I show one example here, and you can see there's multiple steps. And you see sort of the same sort of chemistry that I just showed you for the gas phase, but sometimes some new type of steps show up. So if you look at these different steps, here's the original RDX going through this mechanism here. This is the HONO elimination, so you can see I eliminate NO2 through HNO, I eliminate the second HONO, and I eliminate the third HONO, and I'm left with triazine here. Okay, and then that's going to eventually break apart. Okay, or I could go to this step down here. This is the N-NO2 bond scission. That comes off, and then the weak bond, as I showed you, would be this step, and very similar to what was in the gas phase. One of the steps that end up showing up in the solvation technique that wasn't seen in the gas phase calculations is shown up here. After this first HONO elimination, instead of going through a second HONO elimination, the ring bond opens up right away. Okay, and you start seeing a different type of a route being formed. And you can look at, there's many, in ab initio type calculations, you look at how the structures of the systems look, and you can find different types of processes that occur here. So here's a few more examples of types of reactions that can occur. I can come back with the RDX. I can have, since I'm forming NO in the system, I can have NO displace the NO2 group, and I can form reactions that proceed through this way. If I look at the P4 here, that's an oxidation mechanism via HONO that goes through the system. And if I look at the step down here, this is the hydrogen abstraction reaction by forming first NO2 and then having the NO2 abstract an H atom to form HONO. So there's complications, and what you're seeing is in the condensed phase, it's even much more complicated than of what's going on in the gas phase. But this is some of the initial steps of work that's really starting to look at condensed phase chemistry. And if you look at what people have done, just following that last set of results, you can build then a condensed phase model, and you can go through predictions and calculate how the species will be formed and consumed in the condensed phase. And using those experiments where I mentioned to you about the thermolysis experiments where I heat the foil and I measure what's coming off the surface, I can see how the experimental measurements compare with the calculations. This is still, as I said, very much in its infancy, and there's a lot of significant uncertainty in condensed phase chemistry. Okay, so let me kind of just show you, very similar. I told you, what the structure might look like for a double base repellent. You can see here, if I schematically estimate what you'll see for a nitramine, you see a very similar process. I have the nitramine down here. As the thermal wave goes into the nitramine, I mentioned that there's basically different polymorphs. So I'll go through basically a phase transition, a crystalline phase transition. Eventually, I'll start going to a melt layer where there could be some condensed phase chemistries. I'll start forming some gas bubbles in that condensed phase region. I'll have a fizz zone where I now got a mixture that's both highly gas and some molten material that's around. I go into my initial first stage reaction, primary reaction. I go into a dark zone, and then I go into a second stage reaction. And what you'll see here, I think I got a little movie here, but this region right here on the top of RDX burning, this is this fizz zone, and you can see it build up. It's a foam layer that has both gas and melt layer within it. So if you look right here, you can see the foam layer. This is the flame above the surface, so you can see a separation region between it. So down in here's the foam layer, and again the flame as it burns down. Probably the most sophisticated modeling now has been with RDX combustion, using not that chemistry that I showed you for the detailed chemistry for the condensed phase, but using those two steps and a detailed mechanism for the gas phase, and having that foam layer and accounting for the two-phase region. And the equations for this are also in the appendix. This is some work that Professor Yang at Georgia Tech has done, and I'll just show you some of the results from that as well. Again, if you try to predict the burning rate as a function of pressure, you do a relatively good job, because calculating the temperature profile is not that difficult if I get the heat release right. So these are just a number of different types of experimental results in the prediction of the burn rate. So relatively good over a wide pressure range. If you look at the function as the temperature profile as a function of temperature, you can see how the thermal layer in the condensed phase changes with pressure. So at very high pressures, you have a very thin thermal wave thickness. As I go to low pressures, that thermal wave thickness gets greater. So what that means is, if the thermal wave layer is thick, I have more time for condensed phase chemistry. Okay, as it gets thinner, the time for condensed phase chemistry gets less, because the burning rate has increased significantly. The wave thickness is smaller, and as a consequence, as I go to higher pressures, the vaporization process starts to compete with any condensed phase chemistry. If you look in the gas phase, you don't really see an RDX, the dark zone, that sort of merges together, but you can see that as I increase the pressure, the gas phase kinetics accelerate and eventually come very close to the surface. I make a very steep gradient, so the dTdx at the surface is very steep. The heat feedback into the condensed phase is high, and I increase the burning rate. Looking at some of the predictions of species profiles, again, at these higher heat release rates, you see mainly coming off of the surface the high temperature type products, HCN and NO2 or HONO, and you don't really see the nitrous oxide and the formaldehyde as much. That would happen more in the condensed phase at slower rates, lower pressures. But here, this is the model predictions, and on the right-hand side are some mass spec concentrations that were measured by a Russian group. And again, qualitatively, you can see that in this first stage, the HCN is going away, the NO in the dark zones, which is combined, I'm forming CO and water. So I have a very good similarity in terms of the results. If you look at some other details of the system, as I go to higher pressures, the molten layer thickness gets thinner and thinner, so the model has generally predicted that with the experiment. If I look at the surface temperature, you see this surface temperature going up with pressure again, so it's going to start favoring the vaporization process versus the condensed phase reactions. And I see the amount of void fraction in that foam layer also decreases. So generally, you know, this is the level of modeling that one is at with regards to these homogeneous type components. It's a relatively good understanding of the gas phase. We can predict burning rates generally well if you know the temperature, heat release in the gas phase. But if you start looking at temperature sensitivity, where the details of the chemistry become more important, we can't predict that as well. And that's shown here. This, for example, is HMX. The temperature sensitivity of HMX, as you can see, it decreases with pressure. Again, the model has the right trends. If you look at RDX, it decreases with pressure. Here, basically, the calculation says it's totally independent. And if I look at something like AP, which decreases and then increases, you find that this case is basically also totally independent of pressure. So the modeling calculations are not quite as good in terms of looking at these secondary type parameters. Okay, so let me finish this section by just showing you a few results about our understanding of composite propellants. And this, I'll take something like AP and hydroxyl terminated polybutadiene as an example. So if I look at a composite propellant and its composition, what you'll typically find is the solids loading. If I include aluminum with the oxidizer, it could be as high as 88%, and the binder has about 12%. If you look at the size distribution, you typically, in terms of the oxidizer, it's divided into three size distributions. What's referred to as a coarse oxidizer size, which may range anywhere from about 200 to 400 micron. Medium oxidizer range about 20 to 30 or 90 micron. And the fine oxidizer region from about 1 to 15 micron. Note that the aluminum size sort of fits in between the fine and the medium. So if you were to look at a cross section of composite propellant, you might see something like this. These are the very large AP particles, and then in the binder region, in between the very large AP particles, is where the medium and the fine AP is located. You can see some of that, and if there's aluminum in here, it's also going to fit in that size. So the one thing to recognize is the topology of this is dominated now by these large crystalline oxidizer particles. So the question is, well, how does one go about and start building a model for this? Because I've got this 3D structure, and I'm starting off again not knowing much about the chemistry of any of the individual ingredients. So what typically has been done is, again, apply sort of this hierarchical approach, where first I study the decomposition of each of the individual components, and I start making the geometry more and more complex, so that eventually I'm going to get to this sort of three-dimensional structure with these particles packed over a different size distribution. And so I kind of just summarized this hierarchical approach. So the first thing that one might do is study AP decomposition by itself, and do that in a one-dimensional structure. So I take basically a very simple fluid mechanical situation where the gases are coming off of the top surface of the AP, and I can analyze the composition as a function of distance from the surface, and I can build models then to basically try to see whether or not I understand that chemistry. I can start adding binder components by basically going to a counterflow situation, where now I have a crystal AP sitting on the base here, and I start flowing on the top surface decomposed products from the binder. And what that's going to do then is I'm going to sit up a monopropellant flame above the surface of the AP, but as the oxygen that comes from that monopropellant flame leaves, it'll mix with the fuel fragments coming down, and I'll develop a diffusion flame. Okay, and now I can look at that all in a 1D structure, so it's very easy to analyze experimentally as well as numerically. And eventually what I want to do then is start changing the geometry so that I'm adding complexity to it. So I'm going to go from this 1D geometry to a 2-dimensional geometry, and the type of things that might be done there is I create sandwich propellants. So now I have a slab of, say, HTPB, I put a slab of AP in between it, and then I put another slab of HTPB on the other side. So I have like a simple 2D structure where now I look at the interaction at the interface of the binder and the oxidizer, as well as the monopropellant. And eventually what I want to do then is get down to a 3D structure with realistic packing. Okay. Now, again, you might ask why one wants to understand the kinetics. If you look at metrics, particularly for rocket motors, ISP and flame temperature can generally be calculated from thermodynamics, so I don't really need to know the kinetics. But if I want to know the critical ballistic parameters, such as the burning rate, the pressure exponent, the temperature sensitivity, how ignition and transient combustion is controlled, then I need to know something about the kinetics. And what's kind of interesting in terms of looking at ballistics, a 33% error in the burning rate can lead to like a 300% overpressure in a motor. So knowing, relatively accurately the burning rate, as I told you, it's a very important metric. It is really important in designing rocket motors and propellants. The pressure exponent obviously is important with regards to stability, and global models really can't uncover the details of the real chemistry, and you can't predict this transition, for example, to DDT, ignition, instability, and so really to design future rocket motors a priori from models, you need to know something about the detailed kinetics. So as I said, the first thing that's typically done is to look at the oxidizer by itself. AP's relatively atypical, and if you look at just the AP decomposing as a function of pressure, you'll get a burning rate that looks like this curve here. As I mentioned, it has a low pressure deflagration limit of about 20 atmospheres. Below that, it won't burn, so I need to increase the pressure, and then above it, I'll get a pressure exponent that looks like that. If I mix the AP with a binder, then I can get much larger burning rates out of that combined system, because now I'm taking that excess oxidizer from the AP and I'm allowing it to react with more fuel, so I get more energy out of the system. So AP produces about 30% excess oxygen, and it's a class 1.3, but the negative thing in it has chlorine chemistry, which makes developing models even more complicated. A simplistic view, and I think I mentioned this yesterday, how a composite propellant might burn, is shown here, where I have the large oxidizer particles, and as they burn, since AP looks like a monopropellant, I'm going to have a monopropellant flame sitting above the surface here. So this is going to, if you remember, I'm going to have that proton transfer. The AP is going to decompose to something like ammonia and hydrogen perchloric acid, and eventually, as that reacts in this monopropellant flame, out of the outcome of this, I'm going to have about 30% molecular oxygen up here. Okay, so in the binder region here, if I have very small oxidizer particles mixed in with the binder, what happens is, as they start to decompose, as they come off the surface with the decomposed binder, they mix faster than they can react because of the small length scale. And so I end up sort of forming a pre-mixed flame in the region between the large oxidizer particles. But even though it's pre-mixed, it's a very fuel-rich pre-mixed flame, and so I have a lot of fuel fragments coming out of here, and the fuel fragments then react with this excess oxygen from the large AP crystals to create this diffusion flame. And then in the inner region here, I can have triple flames that make the process of burning very complex. And what you see then is, obviously, if I change the size of these particles, the distribution of the size distribution of the coarse and the medium, you can actually change the flame structure as a function of pressure that changes the burning rate characteristics. There has been models for AP developed. You can see here's one that was developed in 2014. And what I mentioned to you the other day is we still don't understand just AP monopropellant by itself. The solid line here is the most recent model prediction of burning rate as a function of pressure, and it just assumes that the burning rate goes up with pressure and does not capture any of this negative burning rate dependence or, again, positive burning rate dependence. Most rocket motors, however, are burning in this region down here, so this is the most important region in terms of a rocket motor. In terms of a condensed phase model, MC Lin at Emory University has actually developed some condensed phase models for ammonia perchlorate, which goes through a complex adduct and a melt layer, which eventually comes out and, as I said, forms ammonia and hydrogen perchloric acid. Okay, so I also showed you the other day that, looking at AP, what happens at the surface is very complex, and what happens in the subsurface has not been studied very well. There's been different types of studies used where the system has been quenched. Studies where one has looked at using FTIR analysis, what type of species have come off the surface. And mechanisms, again, for the condensed phase are relatively simple. The gas phase chemistry, as one gets further and further away from the surface, is relatively well understood. And so one can develop these mechanisms again. And so I'll spend a couple minutes and then we'll take a break here. But these are examples then of this hierarchical approach of developing this mechanism. So this is a 1D counterflow calculation. So if you look down here, there's a AP crystal, there's a burner tube up here. So I come over here, this is the geometry. This is a pressed pellet of AP particles to create a pellet that's maybe a centimeter in diameter and a little bit longer than a centimeter in length. And what one assumes then in this case, okay, is the binder H2PB is decomposing. It makes butadiene, makes ethylene, and individually one looks at these individual hydrocarbon components flowing against the AP crystal. And when that happens, then off of the AP crystal, you'll see this monopropellant flame, which forms the oxygen, and coming towards it, you'll mix the fuel with that excess oxygen and you'll have a diffusion flame, and you get something that looks like this. So this is the emission from the monopropellant flame, and you can see it's multi-structured, and the diffusion flame then is sitting up here, very little soot formation. And people can then, because of the simple geometry between this point and this point, use laser diagnostics and actually measure in situ many of the intermediate species through this flame structure, and then develop these models and see how well the models predict the species profiles, and again, developing this mechanism. The next level might be then to go to a two-dimensional structure. This is a simple case where the AP pellet, a little hole was drilled in it, okay, and now through this hole, what's being passed is basically decomposed hydrocarbon from the binder. Maybe the simplest one here, again, is methane coming up through the center, and experimentally, this is what you see. Above the AP pellet, you can see the monopropellant flame, and as the methane comes through the monopropellant flame, you form a diffusion flame because of the mixing of the excess oxygen and the methane that's decomposing. And again, one can model this structure as shown here and determine how well the kinetics are known. Okay, let's take a 10-minute break, and I don't have much left in this section, and then we'll move on to the next section. So why don't